Hello and welcome back. Lecture 3-1, Fourier Series. The objectives of today's lecture are to describe how to use Fourier Series to describe a periodic signal, to illustrate orthogonality property for complex exponentials, and to understand the process to find Fourier Series coefficients. Everything we have done in the course up to this point has laid the foundation for what we do today. Fourier Series will be the foundation for everything we do for the remainder of this course, and this is where the course really begins. Fourier series are used to represent periodic signals. It is an expansion of periodic signals in terms of complex exponentials or sinusoids and harmonic frequencies of omega naught. Fourier series are like waves. They are a more efficient way to transfer energy that's just the sum of a series of sinusoids or waves. Let x of t be periodic with fundamental period t naught and fundamental frequency omega naught. The Fourier series can be written as x of t is equal to the summation from k equals negative infinity to infinity, x of k e to the jk omega naught t, which we know we can also write in terms of the imaginary and real part as the summation from k equals negative infinity to infinity, x of k cosine k omega naught t plus j sine k omega naught t. If x of t is real, then x of t can be written as x of t is equal to x of 0 plus the summation from k equals 1 to infinity, 2 times x of k cosine k omega naught t plus the angle x of k, where x of k is called the Fourier series coefficients. In a prior lecture, we saw that the complex exponentials e to the j omega naught t are eigenfunctions of LTI systems. Remember, h of j omega was the eigenvalue. So for the following LTI system, the response due to any periodic signal is presented by the following equation, where the input is e to the j omega naught t, the system is represented by the frequency response h of j omega, and the output is e to the j omega naught t h of j omega. So y of t is the summation from k equals negative infinity to infinity, x of k, h of jk omega naught, e to jk omega naught t. So the product x of k times h of jk omega naught is y of k. This is a Fourier series representation of a periodic signal y of t with Fourier series coefficients y of k. The Fourier series expresses any periodic signal as a linear combination of e to the jk omega naught for k integers. Each of these exponentials is periodic with a fundamental period of the sequence t naught equals 2 pi over omega naught and a fundamental frequency of the sequence omega naught equals 2 pi over t naught. For the following complex exponentials, phi sub k of t equal to e to the jk omega naught t, where k is equal to 0, plus or minus 1, plus or minus 2, and so on, and where phi sub k t plus t naught is equal to phi sub k of t for all k, that means we have periodic signals that are all related by some multiple of k, which we will call our harmonics. If phi sub 0 of t is equal to e to the j0 equals 1, this is called our DC term. So then you would take the DC term times the Fourier series coefficient x of 0. Then you would take the first harmonic, e to the j omega naught t, and multiply it by the Fourier series coefficient x of 1. Then you would take the second harmonic. So notice we now have 2 for every cycle for the first harmonic, and multiply that by x of t, and you would add them all together, and you would continue to do that and see that they're all harmonically related. This is similar to the cover we had with the square wave, where as you add on more harmonics, it starts to approximate that periodic signal. Orthogonality. Complex exponentials at different frequencies are orthogonal. It is possible to use the dot product to verify that these exponentials are orthogonal, and the dot product is given by the following proof. Note that we want these complex exponentials to be orthogonal because we use a linear combination of them in order to approximate periodic signals. So if we have the integral over t naught, which is 1 period of phi I of t, phi k conjugate of t equals dt, we can rewrite this as the integral from negative t naught over t to t naught over t of e to the j I omega naught t times e to the negative jk omega naught t which equals the integral from negative t naught over t to t naught over t e to the j times the quantity I minus k omega naught t dt, which equals 1 over j times the quantity I minus k omega naught times e to the j to the I minus k omega naught t evaluated from negative t naught over 2 to t naught over 2, which equals 1 over j times I minus k times omega naught e to the j times I minus k omega naught t evaluated from negative pi over omega naught to pi over omega naught. Notice here that because t naught equals 2 pi over omega naught, I can rewrite t naught over 2 as pi over omega naught. So this equals 2 over I minus k omega naught times e to the j I minus k times pi minus e to the negative j times I minus k times pi, that entire quantity divided by 2j. And what you should see here is that that second expression is actually a sine. So I can write this as 2 times the sine of I minus k times pi divided by I minus k times omega naught. So what we find here is that this is equal to 0 when I minus k is not equal to 0. Or when I is not equal to k. So that proves that they are orthogonal for I not equal to k. So as long as we have different values for I and k, it won't be orthogonal. So now let's determine what happens when I is equal to k. So if I is equal to k, then the integral over t naught of phi sub k of t, the magnitude squared dt, because remember, when you multiply a function phi sub I of t times its conjugate, it gives you the magnitude squared. Then this would be equal to the integral from negative t naught over 2 to t naught over 2 dt, which equals t naught. So when I is equal to k, you get t naught. So in summary, orthogonal means that the dot product equals the magnitude for I equals k and 0 for I not equal to k. Fourier series coefficients. The Fourier series coefficients for a sequence x of t is x of k. X of k is a set of complex exponentials referred to as the Fourier series. Suppose x of t is a signal that can be written as a Fourier series. So x of t would be the summation from p equals negative infinity to infinity x of p e to the jp omega naught t. So this would be equal to, starting from negative infinity dot 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 plus x of negative 2 times e to the negative j2 omega naught t plus x of negative 1 times e to the negative j omega naught t plus x of 0 e to the j0 plus x of 1 e to the j omega naught t plus x of 2 e to the j2 omega naught t and so on. So we would call x of 0 our DC term, and we would call x of 2 our second harmonic, and x of 1 our first harmonic. Note also that x of negative 2 would be referred to as the second harmonic, and x of negative 1 would be referred to as the first harmonic. How can we find x of k? We're going to use the following process in order to find x of k. So we're going to have x of t times e to the negative jk omega naught t. And we're going to rewrite that as the summation from p equals negative infinity to infinity of x of p e to the jp omega naught t times e to the negative jk omega naught t. So this can be rewritten as the summation from p equals negative infinity to infinity of x of p e to the jp omega naught t e to the negative jk omega naught t. So now if I integrate over one period t naught x of t e to the negative jk omega naught t dt, this equals the summation over the integral over one period of the summation from p equals negative infinity to infinity x of p e to the jp omega naught t e to the negative jk omega naught t dt. And remember, based upon orthogonality, when p is equal to k, we get t naught, and when p is not equal to k, we get 0. So if p is equal to k, then this becomes the integral over t naught x of t e to the negative jk omega naught t dt equals the summation from p equals negative infinity to infinity x of p, that quantity, times t naught, which equals x of k times t naught. So now we can solve for x of k. X of k is equal to 1 over t naught, the integral over one period, x of t, e to the negative jk omega naught t, dt. So the Fourier series coefficient formula is x of k is equal to 1 over t naught, the integral over one period, x of t e to the negative jk omega naught t dt. And the reconstruction formula is x of t is equal to the summation from k equals negative infinity to infinity, x of k e to the jk omega naught t. And what we eventually see is that we may not sum all the way from negative infinity to infinity, but we'll do a certain number of harmonics to approximate x of t. A convenient way to visualize Fourier coefficients is to plot x of k versus k, or x of k versus omega. This plot is referred to as the spectrum. We've already seen some spectrums in a prior lecture. In general, x of k is complex value, so you will need two plots, the magnitude of x of k and the phase x of k. So we're going to create the Fourier series and its spectrum for example 1. So for the following pulse train, x of t, find the Fourier series and spectrum, and you will also examine this same phenomenon in lab. So what we have here is a pulse train that repeats every 8 seconds. So t naught, the fundamental period, is 8 seconds. The fundamental frequency, omega naught, is 2 pi over t naught. So omega naught is equal to pi over 4 radians per second. And x of k, the formula we just derived, was 1 over t naught, the integral over t naught, x of t, e to the negative jk omega naught t, dt. So what we would have here is that's going to be 1 over 8, the integral from -2 to 2 for e to the negative jk pi over 4t dt. So down here, x of k is equal to, when you solve this integral, 4 over 8 times the quantity 1 over -j pi over 4k times the exponential e to the negative j pi over 4k t evaluated from -2 to 2. This equals 0.5 times e to the negative j pi over 2k minus e to the j pi over 2k divided by -j pi over 4k. And this equals the sine of pi over 2k divided by pi over 4k, which equals 2 times the sine of pi over 2k divided by pi over 2k, which can be written as a sinc as 2 times the sinc of k over 2. So one thing to note here is what happens when k is equal to 0. When k is equal to 0, that would give us our x of 0 term. A lot of times students will try to substitute it back into this equation here and quickly see that you get a divide by 0 error. So the easiest way to see what happens for k is equal to 0 is to go back to the original equation. So the original equation now simplifies to 1 over t naught, the integral over 1 period, x of t dt, because remember, now that at e to the j, negative jk omega naught t is just e to the 0, which is a 1. So this becomes 1 over 8, the integral from -2 to 2, 4 dt, which equals 2. So now we can write that the Fourier series coefficient x of k is equal to 2 when k is equal to 0, and it's equal to 2 sinc of k over 2 when k is not equal to 0. So for this example, we're going to put the magnitude and the phase plot together so that we can see how the sinc changes with k. So the horizontal axis is going to be k, the vertical axis is going to be x of k, and the first thing I'm going to do is I'm going to sketch a sinc function and show the 0 crossings. And notice that it dies off, and then I'll do it on the other side. So this is the envelope of the spectrum. The spectrum is actually going to be the samples of this. So the first one is going to be, I have 2 at k equals 0. And then I'm going to have 4 over pi at k is equal to 1. And then at 2, I'm going to have a 0. And at 3, I'm going to have -4 over 3 pi. And at 4, I'm going to have a 0 again. At 5, I'm going to have 4 over 5 pi. At 6, it crosses the 0 again. At 7, I'm going to have -4 over 7 pi. At 8, we have a 0. And at 10, we have a 0. And at 12, we have a 0. And at 14, we have a 0. And then at 9, we'd have 4 over 9 pi. At 11, we'd have -4 over 11 pi. And at 13, we'd have 4 over 13 pi. Now the question becomes, where am I getting these numbers from? Well, remember, my envelope is the sinc of k over 2. 2 sinc of k over 2 is equivalent to 2 sine of pi over 2k over pi over 2k. So that's how I'm coming up with the numeric values. So this is symmetric, so although I won't show them on the other side, it has even symmetry. So all the values would be on the other side, where once again the zero crossings would be at -2, -4, -6, -8, -10, -12, and -14. So now what if we do the magnitude spectrum in terms of omega? So now you would think about this would be x of k omega naught, where the horizontal axis is omega. The first thing I want you to see is that the shape is exactly the same. So here's my sinc again on both sides. Where it's decaying by that shape 1 over t. And now my zero crossings are 2 omega naught, 4 omega naught, 6 omega naught, 8 omega naught, 10 omega naught, 12 omega naught, and 14 omega naught. And the value at 0 is still 2. The value at omega naught is 4 over pi. The value at 3 omega naught is -4 over 3 pi, and so on. So if we wanted to approximate x of t with n harmonics, we would do the following. X tilde of t represents an approximation of x of t, and that would be the summation from k equals -n to n of x of k e to the jk omega naught t. So when we write this out, you would have x of -n e to the -j n omega naught t plus ... x of -3 e to the -j3 omega naught t plus x of -2 e to the -j2 omega naught t plus x of -1 e to the -j omega naught t plus x of 0 plus x of 1 e to the j omega naught t plus x of 2 e to the j2 omega naught t plus x of 3 e to the j3 omega naught t plus ... x of n e to the jn omega naught t. So if we were to put in values here, and I'll start at the third harmonic for brevity, we would have 2 sinc -3 halves e to the -j 3 omega naught t plus 0 plus 2 sinc -1 half e to the -j omega naught t plus x of 0, which is 2, plus 2 sinc 1 half e to the j omega naught t plus 0 plus 2 sinc 3 halves e to the j 3 omega naught t plus ... and so on. So a couple of notes. It can be shown that the Fourier series converges almost everywhere for any power signal, and computer-generated signals can be real valued or complex valued, but all physical signals are real valued, and that's typically what we'll study in this course. We will end this lecture on Fourier series with one MATLAB demo. So here we're going to show what happens as you increase the harmonics in order to approximate a signal. So right now we have no harmonics, or the DC value, which is at 2, which makes sense for our 2 sinc of k over 2. So then here's our first harmonic, which is just a simple sinusoid that is actually centered at 2 because our DC term was a 2. Then we have our second harmonic, third, fourth, and now what you should start to be able to see is that it's starting to approximate that pulse train that we had in the problem statement. And as I continue to increase the harmonics, it's going to look more and more like that pulse train. However, right at those discontinuous points, you notice that's the largest error for the approximation, and that's called a Gibbs phenomenon. So it will actually remain, and it would never go away unless I could actually do this to infinity. However, what happens is that as it gets thinner and thinner, it will get to the point that the power for this signal will be the same as the power for the original x of t, because those points are now so thin that the power is essentially 0. And this concludes lecture 3-1 on Fourier series.